Okay, so I'm going to record this lesson in case you ever need to come back and look at it. I think this is a very important lesson. So what do we got? We've got a function that's inside of another function. Well, how do we take the derivative? We have to use the chain rule. And the reason why it's called the chain rule is because they're linked together. F and G are combined together. So how do we actually do this? We take the derivative of the outside function first, and then you keep the inside the way it is, and we multiply by the derivative of the inside function. So notice, notation-wise, if I'm going to take the derivative, I have to call the derivative h prime. Right? So that's part of the notation we talked about. You need to show that notation. So what's the derivative of the outside function? Well, the outside function is f. So I'm going to take the derivative of f, and then we're going to keep the inside exactly the way it is. The inside function is g of x. And then I'm going to multiply by the derivative of whatever the inside function is. Well, the inside function is g, so its derivative is g prime. And that is the rule, or the setup for the chain rule. So hopefully you're going to kind of repeat this saying every time today. The derivative of the outside, keep the inside function exactly the way it is, times by the derivative of the outside. All right. I don't want you to write this first one. I'll have you write this one here. But this first one's really quick. I want you to watch it so you can see how it goes. All right. So what do? I'm going to take the derivative. So I'm going to call it y prime. Now, my outside function here. Sometimes it's helpful to think about, well, what is the outside function? The outside function is something to the 100th power. It's like x to the 100th power. And then the inside function is the polynomial. So if I take the derivative of the outside, that's the 100 is going to come down in front. That's just the power rule. So if I put the 100 on the outside, then I'm going to take one away. I get 99. There's the derivative of the outside. Then I'm going to keep the inside exactly the way it is. And then we're going to multiply. And here's the important part. Talk about notation. We're going to multiply by the derivative of the inside. Well, the derivative of the inside is just two different power rules. The 3 comes down, gives me 3x squared. And then the derivative of minus 4x is just negative 4. And the derivative of the plus 1 is 0, but I don't have to write the 0. So let's look at this. If this was a test, you have the answer right, but you wouldn't get 100%. Okay? Think about notation. Why would I not get 100% on this? I'm multiplying by the entire derivative of the inside. This isn't multiplying by the entire derivative. It looks like I'm multiplying by 3x squared and then subtracting 4. You need to have parentheses if there's more than one term on this derivative. So these are things that I'm looking for on a test. If you didn't have parentheses, you would probably get a point off right there. All right. Now, I'm going to leave it like this because these two pieces, there's not a lot friendly stuff to simplify. All right. Let's have you guys write this one down. This is a real common type of chain rule problem where you have a trig function and then you have something inside of the trig function, inside of cosine. So I like to use my highlighter at least just to start, and I want to think of, well, what's the outside function? The outside function is cosine. And then I even include that little bracket right there so I can see that, yeah, that is the outside. And what's the inside function? The inside function is 3x minus pi over 4. So here's what I mean by on the test. A lot of students would do this. They'd say y equals, and then they'd just say, okay, cool. I'm going to take the derivative of the outside. So the derivative of cosine is negative sine. Derivative of the outside. Keep the inside exactly the way it is. And then we're going to multiply by the derivative of the inside. So what's the derivative of 3x minus pi over 4? Well, derivative of 3x is just 3. The derivative of pi over 4 is a constant. That's 0. So you don't have to put plus 0 here, but you just have the 3. And then there is one extra thing we can do to clean this up. This 3 can be combined out front. So I'm just going to move that 3 out front. Now, notice, why would I not get 100% here? If this was a test question, I did not indicate what this was. It looks like I took the original function and I just kind of played around with it. You need to tell the person reading your test that that was the derivative. This is y prime. So every single thing that I write down is very important and has to have that notation. And I expect you to do that on homework. I expect you to do that on tests and quizzes when you're doing your work. So please pay special attention to notation. All right.
For the AP test, are they gonna like be looking for notation as well? Like, is that
Oh,
gonna be a
big
big
time.
factor?
Yeah,
Okay.
big time. Yep. So um, something as simple as, like, let's say, it'll come up in a second. I'll note that. But yeah, that's why I'm looking for it is because I know what the AP test is searching for. And if you're trying to skip steps or trying not to, if you're going too fast, that's a big problem. So just so you're aware. Okay. Well, we've got 3 questions here, and our goal is to just get you guys really used to the chain rule and how do we find derivatives. Why don't you try this one on your own? Think of what's the outside function, what's the inside function, and apply the chain rule. All right, let's take a look. So the outside function is sine. I'm going to take the derivative of the outside. So the derivative of sine is cosine. We're going to keep the inside exactly the way it is. And then I'm going to multiply by the derivative of the inside. Well, the derivative of 4e to the x, 4 is just a multiplier, so that's going to stay. And the derivative of e to the x is e to the x. The only way that they could simplify this is taking the 4e to the x and moving it to the front. Now notice the 4e to the x that's on the inside of the cosine cannot be combined with the 4e to the x that's on the outside because this we're taking the cosine of this piece. So that cannot move outside of those blue parentheses. And that's as far as we would go there. All right. On this one, I just want to use a different type of notation, but it's the same thing. So give me 1 second. I want to make a little extra room here. So what's another way that we could use to as notation to basically say take the derivative? Well, here's the thing. You might see this notation where it says d dx of both sides. All that means is find the derivative. But that notation, which we're really going to start getting into in a little bit, is think of this as like y over 1. So d times y is dy, dx times 1 is dx. And remember how that was just the same symbol as y prime? That means take the derivative. You'll understand next week why we're doing what we're doing here. But it's the same thing. This is a chain rule. So what is the outside function? Well, in this case, the outside function is the e to the power of. And then the inside function is x squared minus 4. So the derivative of the outside is exactly what it is. It's just e to the x. We're going to keep the inside function. And then I'm going to multiply by the derivative. Now notice, even though this was in the power, we're going to take and multiply the whole function by the derivative of x squared minus 4. And the derivative of x squared is just 2x. The 2 comes down, and then the derivative of minus 4 stays. So you could stop right there. That's officially the answer. If it was a multiple choice question, they would just put the 2x in front, and it would be written like that. But either version here or here would be acceptable. All right, we're going to definitely do this one together because this has that new derivative that we just talked about in the warm-up. So we have the natural log of 4x squared. Hopefully you can look at this and say, oh, I see the composition. I see the inside and outside function. The inside function is ln. The outside function is ln. The inside function is 4x squared. So, try that again. What is going on? There we go. Okay, sorry about that. Okay, so the derivative of the outside, well, the derivative of ln is 1 over whatever is on the inside. We should actually use absolute value here, but so derivative is 1 over whatever was on the inside. So in this case, it's just 4x squared. And then here's the tricky part. We have to times the entire thing by the derivative of the inner part. So the derivative of 4x squared, the 2 is going to come down. And the derivative of 4x squared is 8x. But something unique happens here with this specific problem, and you won't always get it this way. But remember, this is like 8x over 1, so you have a fraction times a fraction. which multiplying straight across, you get 8x over 4x squared. We don't have to worry about the parentheses here because anytime you square something, it's going to be positive anyways, but don't worry about those absolute values. But I can then reduce this, and 8 divided by 4 is 2 over 1. X on top and x squared on bottom will leave me with just an x on bottom. So you could say your derivative is really just 2 divided by x. So this brings up another good point from our test. You had one of the questions, I don't remember which question, if it was 9, 10, or 11, that you were asked to do the quotient rule and then simplify completely. And a lot of people made a mistake with squaring. Now this is not the way that it was presented on the test, but it said reduce as well. So you need to reduce. If you have 8 over 4, that reduces down to 2 over 1. If you have x on top and x on bottom, you need to reduce. So this is what would be a simplified answer. The thing that I'm thinking about on the test, really quick, I'm just going to erase this, but the test that we just took is you had a problem that I know this isn't the answer, but I'm just going to bring this up. It was you had something squared, so you had like 4x squared. Well, a lot of people wrote this. That's not true. These are not equal, right? What happens is when you square it, you're squaring both the 4 and the 2, which is 16x squared. So that just kind of quick popped in my head as that was an error that a lot of students made, which means it didn't simplify correctly. Okay. This one didn't turn out the way that I wanted it to. We're gonna make this should be an x squared up here. For some reason, didn't come out that way. So now that we know the chain rule, we can ask you this very famous question, which you will be asked pretty much every single test or every single unit. Anytime we learn something new, we're going to ask you to write the equation of a tangent line because you have to know you have to interpret that. Well, what does that mean? And I hope that you see the equation of the tangent line and you're thinking, I need a point, right? I need some x1, y1, and then I need the slope. But isn't slope the same as derivative? You had a question like this on the last test, and I'm going to point out some things that students did wrong, just so hopefully we can not make those mistakes in the future. All right, so what do we have? Find the equation of the tangent line to the graph. Here's the function at x equals 0. All right, well, let's think about that. This is part of a point, right? X is 0. Well, what is y then? Let's just plug it in. Notice my notation. Regular point. What if I plug in 0 here? Well, that's nothing crazy. 0 squared is 0. E to the 0 is 1. So that's how we find y1. Right? That's how I find my point. Now, I believe on the test, we didn't give you x equals. We said f of x is equal to, which means it wasn't x equaled that number, it was the output. And that's a lot of people flipped that around. And I think there was a problem like that on the review worksheet as well. So if you check your answers, you caught that. Okay, so now I need to find the slope. Well, the slope is the derivative. Well, we have to use the chain rule. And this is where we have to think of what is the outside function here. The outside function is e to the x. The inside function is x squared. So the derivative of 5e to the x is just 5e to the x, but instead of putting an x, we're going to keep the original inside piece. And it might even be nice to add your own parentheses around there. So there's the derivative of the outside, and then I'm going to multiply by the derivative of the inside. So what's the derivative of x squared? It's 2x. So again, look at my notation. I used y prime. That tells the person reading this that that is the slope. And we could rewrite it like this. Now here's what I also noticed. On the test, people were really good at finding the derivative and saying, yep, that's my slope. And then they plugged the slope as an equation into an equation. You can't have an equation in an equation. You need the slope, you need the derivative at x equals 0, right? That's the point that they wanted at. So now I have to find what is the derivative at 0. Well, all I'm going to do is plug in 0 for x and simplify. The nice thing is 2 times 0 is 0. 0 times whatever this is, which is just 5, ends up being 0. So there's the slope. The slope is 0, and now you have everything you need to write the equation of the tangent line. Okay, the slope is 0. I'll do y minus y1 times x minus x1. We already know what x1 and y1 are. That's 5, that's 0. Now this is a perfectly acceptable answer right here. You could stop right here. Right? And I actually would encourage you to stop. If you were handwriting your work, I would stop there. If it's multiple choice, then they're going to distribute. And when I distribute 0, I get 0 over here. And then the 5 would come over. So the other acceptable answer is right here. Y equals 5. Now you might even be thinking about, ooh, wait a minute. If my slope was 0, isn't this a horizontal tangent? And we're going to learn next chapter that that's how we find maxes or mins or maybe even a little flat point in the graph. We don't know with really without testing it a little further. Okay. I don't want you to write this next piece. This is more of just kind of an appreciation of where does this new derivative, we're going to learn another derivative today. So we have the chain rule, we have the natural log of x, and then we're going to have a to the x. So don't write this. It's just giving you guys some appreciation of where does this come from. And I'm going to go through it pretty fast. So hopefully you see a to the x is, what if I have a number? Like I could say 3 to the power of x. And how do I take the derivative of that? Well, to do that, we can do an algebraic proof. What if I raise this same thing to e to the ln? Well, don't those cancel out? E and L go away. So hopefully you can see that the right side is really equivalent to the left side. And then I want to take the derivative of both sides. Well, to do that, we need to use a pre-calc rule, which says if you have a natural log, the exponent can actually float right out in front. And that's where this x came from. But why is that important? Now we actually know how to do the derivative of this. And we didn't know it until this direct point. What's my outside function? It's e to the x. What's the inside function? It's x ln of a, and a is a constant, so the natural log of a is a constant. We can use the chain rule right here. The derivative of the outside is e to keep the inside, and the derivative of the inside is ln of a. So that is the chain rule. Right here, the chain rule is what is allowing us to basically find the derivative of this. Now notice, I didn't do anything to the left side because that's what we're finding the derivative of. Well, what if I now undo that and this x that originally came down, what if I put it back up? Then what happens? The e and ln go away, and what's left over is a to the x times ln of a. And there is our proof. So the only part I want you to write down is right here. Add this to your list of derivatives. When you see a to the x, its derivative now is exactly itself, a to the x, and then because of the chain rule, it's times the natural log of the base, a. Okay? This is always a tricky one. It's usually, kids get stuck on this. So we're going to try some derivatives with this new rule. Might even copy it to your.
What's that variable at the end?
A. Yep,
Okay.
it's the same. The base A is the same base A right here. I'll make that a little clearer. That is kind of a little bit messy. I used a thicker point, so hopefully that looks better. So let me show you how friendly this is if you've memorized this or you remember it. All right. Now, the chain rule can be applied here. So that's the thing you have to know is this rule that we just learned, since it has an exponent, it has an opportunity to have an inside function. So the chain rule can and will be applied to a lot of derivatives now. So never, ever forget about the chain rule. All right, look at the format. 2 to the power of a. That's in the exact same form as the new rule we just learned. So its derivative is just plugging a 2 wherever you see an a, and then you're technically done. But I want to show you how you could even still use the chain rule on this. All right, so look at my notation. This is f of x. I'm going to take the derivative. So there's f prime of x. And we're going to do, notice how it starts off. The derivative of 2 to the x is itself times the natural log of the base. And the base is just 2. Now, technically, you're done. But you could think of, there is a chain rule here. The inside function here is just an x. What's the derivative of just x? Well, technically, it's 1. Now, does timesing by 1 change this at all? No. So that's why when it's just an x, we could use the chain rule, but every time it's the derivative of 1, so we don't. We don't write it just because it's just doing extra. So this is just using the fact. Notice it's the same thing times the natural log of the base. All right, what about this one? This one is a little different, and it's different because of the negative. So we actually have to use the chain rule here. Right? The derivative of m of x is going to be exactly the same. So 3 to the negative x times the natural log of the base. But now we have to do the chain rule. Notice, negative x is my inside function, so I'm going to multiply by the negative x, or the derivative of negative x, which is negative 1. And when I wrote out my homework solutions for tonight's homework, I used a red pen and I just said chain rule. So that way you guys knew that I did the chain rule there. So because this is a negative x, we can actually simplify this, because if it was a multiple choice question, it wouldn't be written in the form that it is right there. So here's what I would do. Remember how 3 to the negative x, that negative is just going to bring it down in the denominator? And then the ln of 3 is going to stay up top because there's a positive 1 here. And then the negative 1 is just going to times the whatever's in the numerator by negative 1. So I would, instead of writing 1, I would just put it as a negative. This is what it would look like if it was a multiple choice question.
Wait, so the negative goes outside of the natural log?
Correct. Yep. This is a multiplier, so you would just kind of multiply it. You can think of like a negative 1 times the natural log of 3. We can't do anything on the inside because this 3 is protected by the ln. Same thing as if it was like the sign of a number. You can't do anything with the parentheses, so a number timesing that would just go out in front.
Oh,
All right. So now notice this one. This has a 1/2 as your a value. But it also has an exponent that has a lot more going on, which just means you know you're going to have the chain rule here. So look at the notation. T of u is equal to this. So T prime of u is going to be itself a of x, or 1/2 to the power of, and then we're going to keep the inside. Then we're going to times by the natural log of the base. So all of this stuff that I wrote first is just applying the rule for this derivative. I didn't even think about the chain rule yet. Now the chain rule is taking the derivative of whatever's on the inside, which the derivative of u squared plus 1, well, derivative of u squared is 2u, and the derivative of plus 1 is 0, so we don't write that. And to be honest, the only other way you could write this is take the 2u and put it in front, because the 1/2, they're protected by their brackets and parentheses. And since putting the 2u out in front really doesn't even change the appearance, we're going to stop right there. Okay, now, I hate to tell you this. Recognizing the chain rule is difficult, but once you get the hang of it, it becomes very quick and hopefully friendly. But it does get harder. Because what happens if I have a like a double composition? What if I have an inside of an inside function? And that's what we're going to look at next, is what if we have multiple chain rules to look at? Now, sometimes we do, sometimes we don't. And that's what I'm trying to show you here is, when do we know we have more than one inside function? So our whole directions today have mostly been find the derivative. All right, so first thing I'm going to look at is notice my outside function. That is something to the -5th power. That's just a power rule. So we have an outside function, and then we have just a regular inside function. Nothing crazy right there. So we're going to take the derivative of the outside, which brings the -5 down in front. Now remember, we take one away, which gives me a -6 up here. And then we're going to keep the inside. And then the chain rule part is the derivative of the inside. Well, the derivative of 3 is 0. The derivative of -x is just -1. Then we can clean this up a little bit. So here's how I would clean this up. See how it's a -6? The 3 minus x is going to be brought down in the denominator and made as a positive power. And then I've got the -5 left up top, because remember, this is -5 to the first power. That's going to stay in the numerator, and then that's going to multiply by -1. So technically, it's just a 5 left over. So this was just one chain rule. That's it. What about this one? And I don't love this problem because you can actually do it a different way. I wouldn't directly use the chain rule here, but we're going to do it just so you guys can see how it works. So, and again, watch my notation. One of these days I'm going to figure out how to use this pen smoothly. Now notice, I didn't write prime yet, all right? Because I'm going to rewrite this. This 3 I really don't like. So I'm going to actually pull that 3 out. And that's one of the properties we talked about early on, is if it has cosine to the third theta, you can rewrite it as cosine to the third power on the outside. And that's really helpful. Now, yes, you could just multiply these and you could call this cosine to the 6th power, which is really what I would do. But I want to show you why this works the way it does. And like I said, it's not a great problem. But notice, I have an outside layer of x squared. But then I have another inside layer. Let's use the green. So let's look at the green. The green is just the third power. And then my innermost layer is cosine. So I've got 3 different layers here, which is a double chain rule. All right, so how would we do this? Now I'm going to take the derivative. So I'm going to use the prime notation. And I'm going to take the derivative of the outside, which is the 2. That's going to come down in front. And then take 1 away, so it becomes 1. And then I've got cosine theta to the third power on the inside. All right, nothing crazy there. But now I have to take the derivative of cosine to the third power, but that has a layer as well. So now I'm going to take this 3, I'm going to use parentheses, so 3 times cosine of theta stays, and then we take 1 away. All right, but then I have the innermost part. So this is the chain rule applied again. What's the derivative of cosine? It's negative sine theta. So anytime you're asked to do more than one chain, hopefully you see the linking together. The derivative of the original outside, this is the derivative of the next outside, and this was the derivative of the most inner part. It's like layers. And then we could clean this up because there's some things that actually are common. So notice I've got a 2. a 3 and a -1. That's going to give me -6. And then the sine would actually come next, but it really doesn't matter if I put the sine or the cosine. And then what would be left over is I've got cosine to the third and cosine to the second. That'd be cosine to the fifth. And instead of writing the 5 above the theta, we could put it right in front. So this was a lot longer way, but I wanted to show you the double chain on that one. This one, sorry, this one shouldn't have an x, it should have a theta. So hopefully you can see the different layers in this one as well. The outermost function is the cosine. And then we have the e to the x, right? And I might even try to put grouping symbols around that. Then we've got the innermost part there, which is 5 theta squared. So you can hopefully see the different layers that we have going on here. Let's start with proper notation. G prime of theta. And we're going to take the derivative of the outside part first. So the derivative of cosine is negative sine. And then we're going to keep the inside exactly the way it was. So e to the 5 theta squared. And our first chain rule then is the derivative of the inner part. Well, the derivative of e is e to whatever was originally up there. That's the first chain. And then I have to take the derivative of the innermost part, 5 theta squared. Well, the 2 is going to come down and multiply by the 5. So 2 times 5 is 10. And then theta to the first power, we take 1 away. So there you can see I had to apply the chain rule twice. And then we could just clean this up. Notice how we've got a -1 here and a positive 10. So that'll be -10 theta. And I believe they would most likely write the 10 theta squared, or I mean 5 theta squared, e to the 5 theta squared, and then they would times it by the sine of 5 theta squared. Because multiplication is commutative, meaning you could write this in any order, it doesn't matter if you put the e part first, or the sine part, or even the 10, as long as that the whole thing is negative. All right, we got time for one last problem. And then this is really carrying us on to what we're doing Wednesday and Friday. So what happens now if we have product rules mixed in with chain rules or even quotient rules? Here, you see how there's a quotient? right? You've got a fraction, and we have to use the quotient rule to do that. Well, we're not going to get to the quotient one today, which is fine. But look at here, I've got a product. So I may have to apply the product rule first, or sometimes I have to apply the chain rule first. It depends on how the order is set up. But notice I've got two functions. I've got e to the theta, and then I've got theta squared plus 1 to the third power. So I'm thinking here, hopefully you see the layers in the yellow one. This has a chain rule because 3 is on the outside and theta squared is on the inside. But you also see the product rule. And this is where I think, until you become really, really good at this, I'm going to ask that you show your work. So I've got U, then I've got V. So we know we're going to have to do the product rule. And this is where I would like you to set up the product rule the same way we did when we first learned it. Think of this as side work. So we're taking the derivative of u, nothing special, right? This is e to the theta. So the derivative of e to the theta is itself. And I'm thinking, is there a chain rule here? Well, since this is just like an x, the derivative of x would be timesing by 1. But that 1 doesn't help us, so that's why we don't write it. But now I actually have a chain rule here. Right? You can see the outside function is 3, so we're going to take the 3, we're going to drop it down, and then we're going to keep exactly what was on the inside. That doesn't change. So theta squared plus 1 stays on the inside, and then we take 1 away. So this should have a squared here. And then my last part is to apply the chain rule. So now I have to times by the derivative of the inside. So what's the derivative of 2 theta, or excuse me, theta squared plus 1? Well, the 2 comes down, and we get 2 theta. The plus 1 is the derivative of 0. And I would clean this up before I actually do anything else. See the 3 and the 2? That's going to multiply together to give me 6 theta. And there is now the derivative of the second. All right, so what does that mean? Well, I can now apply the product rule to this function. So I'm going to take the derivative of the first, which was u prime, and we're going to times it by the original second. So e theta times by theta squared plus 1 to the third power. There's the u prime times v, plus, now I have to take the original first times the derivative of the second. All right, so there's my e theta, and then we're going to times this by our new condensed form, 6 theta, theta squared plus 1 squared. Now, let's say this was a test question. You would get points for setting up this work and showing me these 2 steps. You get points for placing the correct spots in the correct product rule. And then you might get 1 extra point if there's any simplifying that can be done. right? But to be honest, there's not, they both have an e to the x in common, so I could factor that out. But then what's left over may or may not help me. So let's take an e to the x, that looks like an equal sign. Let's take this e to the x and this e to the x and pull it out. I should say e to theta. And what's left over then is theta squared plus 1 to the third, that's this piece, plus a 6 theta squared plus 1 squared. And that, the squared and the third, those, I mean, yeah, I could factor out more. I could actually factor out a theta plus 1 squared from each one of these. But at some point, then it doesn't help. It just makes it more confusing. So I tried to simplify it, and it's not really making it look great. I'd just stop right there to avoid any confusion. The simplified version isn't going to be friendlier than this version, so that's why we didn't go further. But every once in a while, it's pretty obvious that things group together. All right, so we're going to save this one for later. But just keep in mind, you can use the chain rule at any time. When you do product rules, when you do quotient rules, sometimes you do a product rule first, like we did. Or sometimes you have to do a chain rule first, and then within that, there's a product rule. So we'll get more exposure to that. All right, so here's what we got. I don't want you to be scared by this, but the homework tonight is right out of the textbook, page 231. It looks like a lot of problems, but it's really just find the derivatives. Find the derivatives. All right. The answers are worked out and posted on our Schoology page. So if you go to the main Schoology page, there's a black folder that says homework answers or worked out solutions, and you'll find it for Unit 3. So I want you to check your work and check for proper notation. Okay? Make sure you're very careful with that.